Hey everyone, and welcome to the beginning of the second half of this course. We are going to begin by looking at Chapter 7, which is about network architecture. So, for network architecture, the first thing we're going to talk about is switches. And switches are like the traffic cops of your network. You've got unmanaged switches, which are like that friend who just goes with the flow, plug and play, no drama, no IP address needed. And then there are managed switches. And managed switches they're the control freaks of the networking. You can configure them through the command line or a web interface. It's kind of like having a switch with a college degree, to be honest with you. We also have layer 3 and layer 4 switches, and those are like switches that went to grad school and can handle more complex decisions. And because we're dealing with switches, let's talk about switch port security. And switch port security's first rule is really to make sure that you disable unused ports. Think of it like locking your front door. You wouldn't leave it open just because you're not expecting visitors, would you? When ports are disabled, they show status messages like administratively down or error disabled, which is basically the network's way of saying nothing to see here, move along. On Cisco or Arista devices, you can use the shutdown command to disable ports and no shutdown to bring them back up. It's like a light switch, but for your data. But here's where things get a little bit more interesting. The switch port-security command line is like having a bouncer at your network's VIP section. It uses MAC filtering to prevent MAC flooding attacks, which basically makes sure that only having one MAC address per port, kind of like having assigned seatings at a concert or a sporting event. But remember, this is just one layer of security. You need defense in depth. Think of it like wearing a belt and suspenders at the same time. It's better safe than sorry. Redundancy in networking is like having multiple routes to get to work. If one path is blocked, you can take another, but there is a catch. Multiple paths can create traffic loops, which are about as useful as a circular driveway that never lets you leave. That's where STP, which stands for Spanning Tree Protocol, comes to the rescue. It's really like a smart GPS that calculates the best paths, and it blocks the ones that would create loops. It calls the best path least cost path, because who doesn't love a good deal on data delivery? Now, this diagram on this slide shows the STP in action. Notice on the diagram there are DP and RP labels. DP stands for designated ports. These are kind of like the popular kids that get to forward downstream traffic. RP stands for route ports. These connect upstream toward the route bridge. Notice how one link is blocked between switch A and switch B. That's the STP saying, not today, loop. No dice. It's kind of like having a traffic coordinator making sure data doesn't get stuck going in circles forever. Now, STP uses BPDUs, which stands for Bridge Protocol Data Units, to communicate between those switches. Think of BPDUs as kind of like gossip between switches. That one may say, hey, did you hear? Switch A thinks it's the root bridge. Switches can be really in 5 different states. The blocking state, which is really doing nothing. The listening state, which is the eavesdropping state. The learning state, which is studying for the test. The forwarding state, which is the actual working state. And then disabled, which is kind of like taking a nap. Those are the 5 stages of switch ports. STP has gotten some upgrades over the years. We've got RSTP, which is Rapid Spanning Tree Protocol. Then there's TRILL, TRILL, which stands for Transparent Interconnection of Lots and Links. There's SPD, which stands for the Shortest Path Bridging. And some manufacturers create their own version of STP, like networking's version of kind of a secret family recipe. So when we start looking at hierarchical design, we're looking at three-tiered architecture, and that's networking's version of kind of a corporate hierarchy. At the very bottom, we have the access layer or the edge layer. These are the work group switches directly connected to the hosts. Think of them as the entry-level employees doing the day-to-day work. The distribution layer or aggregation layer is middle management. They're highly redundant and it connects multi-layer switches. And at the very top is the core layer, and that's kind of like the executives that handle backbone traffic with high efficiency. It's kind of like a well-oiled company, but with fewer meetings. This design is really kind of brilliant because it treats local traffic differently from long-distance traffic. East-west traffic flows between peers in the same network. Think like neighbors chatting over the fence in the backyard. The north-south traffic has to leave the local area to reach its destination. That's like calling your cousin or your grandma or some other extended family member in a different state. By handling these differently, networks become more efficient. It's like having express lanes on the local roads. So here's a graphic of our three-tier network. The distribution layer is like the hub of a wheel, connecting everything together. It's the interface between the core and the access layers, and it also connects other network blocks. Think of it as the networking equivalent of a major airport. Everything connects through here, and it's designed to handle lots of traffic efficiently. Now, modern networks are getting kind of a makeover. Instead of three layers, we're collapsing the core and the distribution into one layer, calling it the spine. It's like combining middle management with the executives, makes it more efficient and less bureaucracy. Now, the spine switches connect to all the leaf switches in a mesh topology, but they don't talk to each other directly. It's called the spine and leaf architecture. Leaf switches often live in the same rack as the servers. We have TOR, which is the top of the rack, and EOR, which is the end of the row switching, basically deciding whether the switches sit on top of the server rack or at the end of the row. Here's a graphic of the spine and leaf design, and it's pretty simple. 2 layers instead of 3 means more efficient access between any 2 network resources, like having a direct flight instead of a layover somewhere. Every leaf switch has a direct connection to every spine switch, creating multiple paths and reducing the number of hops that data needs to make. And here's a real-world example of the spine and leaf architecture. The leaf switches are sitting pretty at the top of each rack, hence the TOR or the top of rack switching. The spine switches up top connect to all of the leaf switches below, kind of like having a well-organized warehouse where every aisle, which would be the leaf, connects directly to the main distribution center, which would be the spine. So why is spine and leaf so popular? There's a lot of benefits to it. Improved redundancy means better reliability. Decreased latency, which means faster performance. Increased scalability means room to grow. Enhanced security and reduced costs. It's basically the network equivalent of having your cake and eating it too, if the cake also made your network faster and more secure. So let's talk about availability. How consistently your network shows up to work. High availability, HA, means your system is like that reliable friend who's never late. It functions nearly all the time. Uptime is how long your system works between failures. On Linux or Unix, you can check uptime with the uptime command. On Windows, it's in Task Manager. It's like checking how long your car has been running without breaking down. Fault tolerance is your network's ability to keep going when things go wrong. Kind of like a superhero who just keeps fighting after repeatedly getting punched. A failure is when your system doesn't meet performance standards, while a fault is when one of your components breaks. Think of it this way. If your car's radio breaks, which is a fault, you can still drive, which is not a failure. But if your engine breaks as a fault, you're stuck, and that's the failure. The goal is to prevent faults from becoming failures. Kind of like having a backup engine for your car. Link aggregation is like having multiple lanes on a highway instead of just one. You combine multiple network interfaces to act as one logical interface, and it goes by different names. Port aggregation on Unix and Linux because they like to be different, or NIC teaming on Windows because Microsoft likes Teams. The benefits are more throughput, automatic failover, and load balancing. It's like having multiple checkout lanes at the grocery store, faster service, and if one breaks, you've got backups. So here's a graphic of what link aggregation looks like in action. See how the server has two NICs bundled together? This lets two workstations communicate with the server simultaneously, like having two phone lines so you can talk to your mom while your teenager texts their friends. The switch sees this as one connection, but underneath, there's redundancy and there's also extra capacity. It's networking's version of why choose one when you can have both. Load balancers are the traffic directors of the network world. They distribute traffic intelligently among multiple devices, making sure everyone carries their fair share of the load. No one likes the coworker who disappears when there's a lot of work to do. Clustering groups redundant resources so they appear as a single device. It's kind of like a boy band that harmonizes so well they just sound like one voice. Web clients connect to a VIP, which is a virtual IP address. That represents the whole cluster. It's like having one phone number that connects to an entire customer service team. This diagram shows clustering in action. Two web servers work together to host a single website, and clients connect through a load balancer to a virtual IP address. It's like having two chefs in a kitchen working together to serve one restaurant. If one chef gets sick, the other keeps the restaurant running. The load balancer makes sure orders are distributed fairly between both chefs. Next, we're going to look at virtualization. And I want you to think of this as the ultimate magic trick, making multiple computers appear on one physical machine. A host is the physical computer doing the heavy lifting, while guests are the virtual machines living rent-free on top. A hypervisor is like the landlord managing all of these virtual tenants. Type 1 hypervisors installed directly on bare metal. They're the serious, no-nonsense type. And Type 2 hypervisors install as applications on a host OS. They're more like the friendly roommate approach to virtualization. When creating a VM, you get to play computer architect. You assign the guest OS, the amount of memory, the hard disk size, the processor type, and other options. It's like building a custom computer, but without the risk of electrocuting yourself or losing tiny screws under your desk. The hypervisor handles all of the resource allocation, so you can focus on the fun stuff, like deciding whether your virtual machine needs 4 gigs or 8 gigs of RAM. Every virtual machine gets its own virtual NIC. Think of this like a digital network card that operates at the data link layer. VMs can have multiple VNICs depending on what the hypervisor allows. It's like having multiple phone lines. And when you select a VNIC, the hypervisor creates a connection between the virtual machine and the host called a bridge or vSwitch. One host can support multiple virtual switches, all controlled by the hypervisor. It's like having a virtual network department inside your computer. So here's our virtual switch in action. We've got 4 VMs connecting through the virtual NICs to a virtual switch, which then connects to the physical network through the host's physical NICs. It's like having an apartment building where each apartment, which is the VM, connects to the building's main electrical panel, which is the virtual switch, which then connects to the city power grid, which is the physical network. Everyone gets power, but it's all managed centrally. VM networking has 3 main modes, like choosing your social media privacy settings, really. Bridge mode is like being completely public. Your VNIC gets its own IP address from the physical network's DHCP server and can talk to anyone. NAT mode is like having a protective parent. Your VM relies on the host to act as a middleman for all network communications. The VM gets its IP addressing info from the host, who handles all of the outside conversations. This diagram shows bridged mode in action. The VNIC communicates directly with the physical network. It's like having a direct phone line instead of going through a switchboard operator. Each VM gets its own IP address from the DHCP server, just like any other device on the network. The virtual switch acts as a transparent bridge, making the VMs appear as if they're physically connected to the network. Host-only mode is like having a private family group chat. VMs can talk to each other and their host, but they cannot communicate with the outside world. The VNICs never use the host's physical NIC. It's completely isolated. This mode is less common than the NAT or bridged networking, kind of like how video calls are less common than texting. Virtualization software gives you the flexibility to create different networking types on one machine. It's like being able to switch between different social circles at will. Virtualization has some serious advantages. Efficient resource use means getting more bang for your buck. It's kind of like carpooling, except for computers. Cost and energy savings because you need fewer physical machines. Fault and threat isolation means if one virtual machine gets a virus, it's quarantined like a sick patient. And backups, recovery, and replication become simple. It's like having a save game feature for your entire computer. But virtualization isn't all sunshine and rainbows, because compromised performance can happen when you're sharing resources. It's like having to share pizza with more people. Less pizza for you. Increased complexity because now you're managing a virtual and a physical infrastructure. There's higher licensing costs because software vendors want to get paid for each virtual instance. And the dreaded single point of failure. If the host goes down, all VMs go down with it. It's like having all of your eggs in one very sophisticated basket. Next, we're going to look at network functions virtualization. NFV is where physical and virtual network architecture becomes friends. It's the process of virtualizing networking features to provide flexible, cost-saving options. Virtual devices can be quickly migrated from one server to another during hardware failures, and resources are used more efficiently, and services can be easily scaled. Next is software-defined networking, shortened to SDN. And SDN is the control freak of the networking, but in a good way. It's a centralized approach that removes decision-making power from individual network devices, and it handles it all at the software level. An SDN controller becomes the puppet master, integrating control of all virtual and physical devices into one system. It can make automatic configuration changes based on network conditions. This is called application-aware networking. And it's like having a really smart traffic control system that adjusts lights based on real-time traffic. SDN organizes network functions into different planes, kind of like organizing a company into different departments. The infrastructure plane, which is the data plane, handles the actual movement of network messages, and that's kind of like the workers on the factory floor. The control plane makes all decisions, which I would equate to kind of the middle management. The application plane is where the SDN controller talks to network applications using APIs. And I would say that those are really the corporate suite having board meetings. And then the management plane handles monitoring and configuration, which is kind of like HR keeping track of all the employees. So here we have a diagram showing how the SDN planes work together. Each plane has its own job and its own communication methods. The application plane uses APIs to talk to the control plane, which uses protocols like STP and ARP to communicate with the infrastructure plane. The management plane keeps an eye on everything using protocols like SSH and SNMP. It's kind of like a well-orchestrated symphony where every section of the symphony knows their part. Last slide on SDN. SDN controllers designs vary based on several factors. It's like choosing a car based on what you want. How centralized is the control plane? What's the level of virtualization support? How many switches can it handle? Can it work across WANs? How does it scale? What security feature does it offer? Can it provide centralized monitoring? It's like creating a dating profile for your network. You really want to find the perfect match. Now we're going to shift gears and look at cloud architecture. And we're not talking about those fluffy things in the sky. We're talking about cloud computing, it's the flexible provision of data storage, applications, and their services over a network. Most cloud providers use virtualization to supply services, kind of like how a restaurant uses different chefs to make different dishes. It's computing on demand, delivered fresh to your digital doorstep. Cloud computing has 5 essential characteristics, kind of like the 5 basic food groups, but for technology. On-demand service is one of them. It means that you get what you need when you need it, kind of like having a 24/7 vending machine. Next, we have broad network access, and that means you can access it from anywhere that has an internet connection. Third, resource pooling means sharing resources efficiently, which is kind of like carpooling for computers. Fourth, we've got metered service, and that means you pay for what you use. No more, no less. And then last, we have rapid elasticity. That means scaling up or down without breaking a sweat. Kind of like having stretchy pants for your data. Cloud service models are different department, or they're like different departments or different apartments, and the rental types of apartments that you can get. We've got on-premises, and that's like owning your own house. You handle everything. Good, bad, ugly, it's your problem. We have IaaS, which is infrastructure as a service. That's like renting an unfurnished apartment. You get the basic structure, but you bring your own stuff in. And then you have the platform as a service, which is PaaS. That includes everything. That includes furniture, utilities. You just need to bring your applications and your data. That's like renting a furnished apartment where all you do is bring your clothes. Everything else is there. Continuing in our apartment analogy, We've got SaaS, which is software as a service. That's like staying in a fully serviced hotel. Everything's provided, and you just show up and use it. And then we have XaaS, which is anything as anything as a service. It's like having a personal concierge who can provide whatever combination of services you need. And the shared responsibility model defines who does what, like splitting chores with roommates, but with clear written agreements so nobody argues about who forgot to take out the digital trash. Cloud deployment models are like choosing where to have your party. Public cloud is like renting a banquet hall, which is a shared space, professional service, open to the public. Private cloud is like hosting at your own house. You have more control, more privacy, but you handle everything. Community cloud is like sharing a clubhouse with a few friends. It's cost effective and it's semi-private. Hybrid cloud mixes public and private, like having some events at home and some at the banquet hall. And then multi-cloud is like using multiple venues for different parts of your event. There are several ways to connect to your cloud, like having multiple ways to order your pizza. You can use a GUI console through a web browser, the point and click approach for visual people. You can use the command line interface for those who like typing commands, and those are for the I don't know what I'm doing approach. You've got the SDK, which is the software development kit. Those are for developers who want to build custom apps. And then you got APIs for programmatic access, which lets applications talk directly to the cloud without human intervention. Cloud services come in 4 main categories, like the departments in a digital department store. Compute capabilities provide virtual machines and processing power. They're kind of the engine room. The networking services handle connectivity and traffic management. They're the highways and bridges. Storage provides space for your data. That's the warehouse. And then security keeps everything safe. Basically like a digital security guard working 24/7 to protect your data. Next, we're going to look at automating networking or networks. And this is a dynamic inventory that constantly adapts to changes, kind of like a GPS that automatically updates when new roads are built. Pipelines support different phases of software development, kind of like an assembly line for code. We've got the IAC, which is the infrastructure as code. That lets you create and manage cloud resources using text-based commands in configuration files. And that's like writing recipes for your network infrastructure. If you follow the recipe, you're going to get consistent results every single time. Automation and orchestration. Automation's like really having a really reliable robot assistant. It's a programmed response to specific events, like automatically patching systems, applying updates, resizing resources, or detecting attacks. Orchestration takes automation to the next level by coordinating many tasks in complex workflows. Think of automation as teaching your robot to make coffee, while orchestration is teaching it to run an entire cafe. The collection of tasks is defined in templates or playbooks, like detailed instruction manuals for your digital workforce. Automation and orchestration provide some serious benefits. Responsiveness and agility let you adapt quickly to market demands, kind of like being able to pivot faster than a basketball player. Better control means fewer human errors. Lower costs because robots don't need any kind of breaks or vacation time. Enhanced security through consistent application of security policies, and repeatability ensures the same tasks are done the same way every single time. So source control is like having a time machine for your code. It tracks and manages changes so you can develop, test, integrate, or even reverse changes as needed. The central repository is like the official library that holds the authoritative versions of code, especially the production version that uses is what users actually see. And then when developers make copies for testing, they create branches, which are like photocopies of a book so that multiple people can work on different chapters without interfering with each other. And when developers upload changes to their branch, it's called a commit. That's like saving your progress in a video game. When changes get incorporated into production, a new version is created and documented. Multiple branches can run concurrently, and development work is coordinated so teams aren't stepping on each other's toes. It's like having multiple editors working on different parts of a magazine simultaneously. Okay, 30 minutes, 47 seconds, not too bad. Congratulations, we've gone through Chapter 7, which has been about network architecture. You should know how to configure switches, explain virtualization, summarize cloud computing, and understand automation well enough to be friends with robots. You should be ready to build networks that are reliable, scalable, and maybe even a little bit fun. Remember, in networking as in life, it's all about making the right connections. That's it for Chapter 7. I will see you in Chapter 8.